Hello and welcome to Lecture 5. Let me make sure that sound is actually working. Yes, it seems to be. Alright, so let's get on into it and let's make sure I turn off my notifications too. First things first, I want to talk about the midterm. So remember that it's going to happen on the 22nd. So I have changed my plans after talking to a lot of people in the department and also you guys. So first of all, it's going to be on Gradescope. It's going to be called Midterm 1. It's going to be placed right here. I'm not sure if you can see it right now, but this is what it looks like. It'll be called that, and you can go and find it on at 10:30 a.m. on April 22nd at the soonest. So, of course, like I said before, it's open book, open notes. Just please do it individually. So it's going to be a timed exam, and you can do it anytime within 24 hours. So starting at 10:30 on April 22nd is when you can start it, and you can finish it up until 10:30 a.m. on April 23rd if you'd like, but you have to do it in an 80-minute time span. So you have to start and then finish it within 80 minutes. Unless you've, of course, requested for DSP accommodations, then you'll have more time. So I'm going to be on Zoom from 11 a.m. to 1 p.m., so essentially the class time on April 22nd, so the day that it's supposed to have happened. And I'll be there to answer your questions. So please use my office hours page Zoom link for that. And if there are any TAs and tutors working on Monday as well, they'll be also there to answer your questions. You can also post on Piazza if you'd like. One thing that I'd like to tell you now, though, is if you don't take this during the class time when I am available to answer your questions, and you end up asking something on Piazza, it's very possible that your question will not be answered in time. That's just something we're going to have to deal with, and I'm sorry about that if you can't take it at the same time as the class. But I just want you to keep that in mind. You will need this operator precedence table, and I've linked to it right here on the exam. I've also linked to it in the exam if you forget about this page. So everything else is the same, and that is all the logistical stuff. So it's going to be a timed exam for 80 minutes, but you can complete it within an entire 24-hour day-long window. Okay, so with that, now we can get into today's lecture, which finishes off the stuff that I was talking about at the end last time, that separate compilation stuff. So first, just a random fact that you will need later. So what is the correct way to test for approximate equality? For example, we want to say that within a certain range, like 0.01, numbers are approximately equal. So things like, I don't know, 14.999 is approximately 15, right? 0.000 with that much precision. So that's the kind of thing that we want to be able to check for. And I want you to think about which of these, and potentially many of them, correctly check for approximate equality within a certain range. So I assume that you've now thought about this, and let's go through the answer. So let's assume that we have a certain number on our fancy number line that we're looking for, and the idea is we want to consider things that are approximately equal to this number, so within a certain fuzzy range, like between here and here. So like, I don't know, 15.001 and 14.999, for example. Inclusive or exclusive, it doesn't really matter. And that is a horrible looking 0, so let me do that again. That's not an eraser. There we go. Slightly better. So that's the idea. And let's just go through these. So absolute value, subtract them. Is that less than a certain range? So that's like finding the difference right here, the distance between those two numbers, and that's totally correct. So A is a possible answer. Then same for y minus x. We're just checking for that to be within an inclusive range this time. And again, that's not a huge deal because absolute value, if you do that minus that versus this minus this, it gets rid of the negatives. And again, we're just looking for whether or not the distance between here and there is very small. It doesn't have to be exclusive, it doesn't have to be inclusive, it doesn't really matter. Now this one, this is a fun one. So A and B are definitely an answer, so your options are D and E at this point. Now, let's talk about this one. This one is not actually an answer. C is incorrect, and so the answer is in fact D. And let me write that right now. So the answer is D. And why is C not correct? Why does that not check for approximate equality? Well, let's replace absolute value x plus y with just a variable called, I don't know, z. Okay, so every time you see absolute value x plus y, I'm going to write z. So this is essentially asking, is z less than z, that is not a z, z plus 0.001. And okay, let's subtract z from both sides. Then I end up with, is 0 less than 0.001? And yes, this is true. This is actually always true. So that's kind of a trick. This is always true. So it didn't really matter what x and y were. This is not really going to help with that idea. Okay, so this does not check for approximate equality. I wouldn't ask you something this tricky on a test, but I just want to make sure that you understand that this is the kind of thing that you should be checking. And now let me talk about why approximate equality is useful. Your floating point numbers are not perfectly exact. You should never be checking for that kind of equality. You should never check for exact floating point equality, because sometimes you just can't represent a certain number. So use approximate equality for doubles and never double equals. Okay, so that's that. And let me show you why. So let me go to Python, just for fun, and let me make a list. I'll call it L, and it'll hold 0.1 10 times. You can't actually do this thing in C++, that's why I'm doing Python. So here's a list with 10 0.1s. I assume that you would expect the sum of this to be 1.0, and that would be a valid assumption. But let me tell you right now that that is incorrect, and we cannot actually represent that answer with perfect precision. We have a lot of decimals of precision, so like if you use 0.001 as your cutoff, you would round and have approximate equality, but you would not end up with exact equality. And this is just an issue with floating points. You just don't have enough space to hold all of the decimal points. Sometimes you can't exactly represent some numbers. You can't exactly represent some numbers with doubles. And there's some kind of error that gets added on when you do this kind of addition, because you can represent 1.0, but once you start summing these together, it's you start losing some precision. So that's the idea there. And now let's go back to our normally scheduled stuff. So here's something like what we did last time. Let's write another function that draws a triangle now instead of a square. So let me go back to our code and change any function that would print out a triangle. We want to instead return a string that represents that triangle. So we made something very similar to this with draw square last time, and so I'm going to copy that over into today's stuff, and I will make a new folder for lecture 5. And let's make a file called, I don't know, this should be, I think, let me scroll ahead for just a second. It should be called draw shapes, possibly. No, just shapes. I'm going to call it shapes.cpp. Okay. And I think that's all I need for right now. So I'm going to copy in most of the stuff from last time for square drawing, because we can keep the squares. We'll just do triangles now instead. So the idea is, let's also declare a draw triangle function. It'll also take a size, and it'll return a string that is a triangle. Okay, that's the idea. It's going to return a string representing an isosceles triangle with a given width. And so 5 here is the width, and that is the maximum number of stars on the end there. So that's 5, then 3, then 1 at the very top. So let us go into this, and instead of n, let's call it width. And then let's go down here, and it's another shape. It's made a little differently than squares, so let's make our own function all over again. So we should definitely start out with an empty string again. Okay, and we'll just build up our final answer into that string, and then we can return it at the very end. Okay, so that's the stuff that remains the same. And now there's a question of how do we actually write this out? So the idea is every time we want to draw a triangle of a certain width, well, first of all, we need to make sure that our width is a certain kind of number. Because let me pretend to draw a triangle of width 4. Those are my best attempt at stars. It's impossible to go in between these two characters to put the final star, isn't it? I can't go in between, I can't have fractional characters because this is 1, 2, 3, 4's characters, this is 1, 2, and I can't go in between those two. Okay, so we should always, first of all, make sure to check that our width is an odd number. And we shouldn't have like negative numbers too, so it should be odd and greater than 0 as well. Greater than or equal to 1, let's say. Okay, because then we could have a triangle of stars, a single one, practically a triangle. Then the next possible one we could have is a width 3, and then we could have a width 5 one. And those would all make sense. 2, 3, 4, 5, 1, 2, 3, 1. Because then there's always a middle. That's the idea with oddness. Okay, so let's take care of that. Let's make sure that if if the width is well, first of all, it needs to be odd. So let's make sure that it's odd. So if it's odd, then mod 2 will not be equal to 0. And we want to make sure. Oh, but let's return if it's even. Actually, let's if width is not odd, or if it's less than. So we want to start at 1. So if it's less than 1, then return empty string. Let's say that'll be our error case. So if it's not odd, that means it's even. So mod 2 is 0. Or if the width is less than 1, we should just immediately return the empty string. But in this case, result is already the empty string. So we could still return result if we wanted to, but I'll keep it as the empty string just for keeping things clear. So if we got this far, if we didn't return yet, we have a valid input, a valid width value. Okay, and then now we can make our triangle. And so the idea is, well, I want to start drawing this triangle. Oops, I'm going to the wrong dimensions. I want to start drawing this triangle always with that final width in mind. So there's going to be some spaces before the first star, then there's going to be some spaces on the second line, and then there's going to be no spaces on the final line. That's the idea there. So let us start with implementing that idea. So let's do just like we did for draw square, where we have a nested loop. So we'll have our outer loop worry about the current line that we're on, because we always need to draw a certain number of lines. So if width is width equals 1, we have 1 line. If width equals 3, we should output 2 lines. And if width equals 5, we should output 3 lines. So see if you can figure out the pattern here for how many lines we need to eventually output. It involves a bit of weird integer division. It happens to be width divided by 2 and plus 1. That's the idea, because when it's 3 divided by 2, integer division is 1 plus 1, 2 lines. 5 divided by 2 is 2, with integer division that is, plus 1 is 3. So that's the number of times that we're going to output. Or we could think about this another way. We can start with the number of stars that we need at the very end, and then constantly subtract 2, because we have to subtract 2 stars each time. Okay? So that's slightly easier, I think. So let's start with that. I think the idea should be that we can also increment. So on the first line, we need to draw 1 star. On the second line, we always need to draw 3 stars, and on the third line, we always need to draw 5 stars. So perhaps we can keep track of how many stars we need to draw on a certain line. So if, let's start out our loop. So for int stars to draw equals, starts out with 1, and it's eventually we want to stop the loop after we've drawn with width stars. So while stars to draw is less than or equal to width, and then we're going to increment every line by 2 stars because we draw 2 more each line. Stars to draw plus equals 2 because we draw 2 more stars with each line that we're on. Okay, so the idea is we do want to add a certain number of stars to the result. So result plus equals a star character. We kind of want to do like times stars to draw. But this is a Python only thing. You cannot do this in C++. Okay? So we have to find another way to draw a certain number of stars. So in this loop, we need to add stars to draw, that many stars, to our result variable, along with a new line. So result plus equals new line as well. So let me figure this out right now. So let's draw stars to draw. So on the first line, we're going to draw 1 star. On the second line, we're going to draw 3 stars. And that'll be another for loop. So for int I equals 0, I is less than stars to draw. So we're going to iterate stars to draw times, is what I'm saying here. I plus plus. And each time we're going to add 1 star because we don't have that kind of multiplication of strings or characters like we might in Python. So we have to use a loop to add multiple stars at a time. And that'll give us a certain amount of correctness here. So the idea is, well, let us get the width from the user again, and then instead of draw square, let's do draw triangle. So let's now compile and run this. G++ shapes.cpp-o shapes. /shapes. Let's do 5, I think. Or wait, do we ask? Yeah, we ask the user. No command line arguments. So let's do 5. Yes, let's do 3. That's not quite right. And we could actually make some tests to make sure of that. So let's use test-driven development again. So let's go back to our separate compilation stuff, tdd.cpp. Let me bring in our assert true function, our good old assert true function. I'll just put it up here for now. Or you know what, let's be fancy. Let's make a declaration and then bring this below. So I had some tests. I could definitely make sure that this was working right. For example, I could have a test that makes sure that our first for a draw triangle, of size 1 works properly. And same for other things. So I can comment this out and actually make some tests instead. Let's write tests for our draw triangle function. Okay, so then let's bring this on down into here and let's write our first test. So assert true. Let's say draw triangle 1. That can be the name of the test. And we want to make sure that draw triangle, when called with the 1, is equal to this string. 1 star and then 1 new line. And that's the idea. That's what we want. Then let's do some fancier tests. Let's make sure that draw triangle 2 is the empty string, because that's what should be happening, right? That's an invalid argument. Draw triangle 3 should look like this. It should be 1 star, a new line, 3 stars, and a new line. But that's not actually correct. we want to put some spaces here first, don't we? And just for symmetry, I'll put a space on the other side as well. So let's pretend that the answer for draw a triangle of width 3 is space star space and then 3 stars. And then we'll do the same for 5. And that is the idea. We'll write all these tests, and those, once they pass, we'll make sure that things are working. So on the very last line, we should have 5 stars for that one, and some spaces in between on the second line, and some extra spaces to center that star on the first line. So that's what should be happening. And these are tests that make sure our draw triangle function is doing what we want. And right now, I think that 2 of them will pass. The first 2. Now we need to worry about centering these stars, okay? And the idea now is, well, how many spaces do we need to offset the amount of stars we're currently outputting? And the idea is to notice the symmetry. So if the width happens to be 5 and I'm on the first line, I know that the number of stars that I need to draw is 1. Subtracting that from my width, I get 4, and if I divide that by 2, I get the 2 stars that I need to print on the left, and the 2 spaces I need to print on the left, and the 2 spaces I need to print on the right. So let me put that into code here. So to know how many spaces we have on the left and right, we subtract from our width the number of stars we're drawing on our current line. So you can see this is a lot fancier than this draw square function. We're doing a lot more now. So we're drawing spaces as well, and to notice how many we need to draw, int spaces on each side of the stars is, well, it's width minus the stars we're currently drawing. That's how many space slots we have, and we want to be symmetric, so we have to divide that by 2. And when we get that, then we know how many spaces to put on the left and on the right. And then I can copy this, this kind of adding spaces, this adding stars code, to instead add spaces. So draw this many spaces on the left, put that in our result variable, and then do the same thing on the right. Okay? So now if, for example, our width is 5 and we're on our first line, then we will draw 5 minus 1 divided by 2, which is 2 spaces on the left, 2 spaces on the left, and 2 spaces on the right. That's the idea there. Okay. And let's see what happens now. If I compile and run this, we get passing tests, and it's always good to write a bunch, but this is enough to convince me that things are working. Okay? So I hope that makes some sense, and this is an example of using nested loops to do fancier things. That'll be helpful for your next lab. Now I want to get into the compilation process again. So we talked a little bit about this separate compilation idea last time, but there's a lot more to it. We were missing a bit of motivation as well. So the idea is you're writing a program, whatever it's called, you give it to the compiler, and it eventually makes a program that you can run. It's called an executable. It's machine code, of course, and its data is a bunch of 1s and 0s. That's called binary. And it started again from source code, which was high-level language, C++, stuff that you can read as a human, but your computer has no idea what to do with in terms of running it. You got to compile it first. So that's the compilation process at a high level. Let us zoom in now, because G++ is doing a lot of stuff under the hood for us. So one thing that it's doing is it's compiling down our code into what's called assembly. That's what .s means, assembly code. And it's giving that to something called an assembler to make a compiled version of just that one file that we gave it. Okay? And all that stuff is then linked together with any library code, like maybe your math library or IOStream to do some printing. And that's all given then to the linker that brings all that stuff together to finally output your program. So let's talk about that just briefly. So G++, I want lowercase g, please. When it compiles every file separately, that's what compilation means, into machine code. It passes through a language called assembly code, which is the last stage of human readable source code. So assembly is a language, a programming language that is specific to your type of CPU that you want to compile for, because different CPUs have different kinds of instructions. So assembly is a programming language that's specific to your type of CPU, and every line, you say, of assembly code corresponds to one CPU instruction, more or less. This is a good high-level idea of what assembly is doing. G++, after it compiles each file separately, it does what we call linking. Links together all the files as well as the compiled libraries, which sit somewhere else in your computer. That's why when you include something in your current directory, you use these single quotes, and when you include something like IOStream, you use these special angle brackets. That's how you tell C++ to use these fancier libraries that are pre-compiled and ready for you to use. Links together, so G++ is going to link together all of these files, as well as the compiled libraries, into one final runnable executable program. So this is the key here. And this process is called the linking process, and it's done by the linker, we say. So compilation is really taking a single program file, a single .cpp file, and bringing it down into machine code. And we overuse this term very commonly. We just say that we're compiling something, we're bringing it all the way down to an executable program. And that's more colloquial terms. So compilation is something that happens before linking, really. So it's in C++ at least, it's taking a single program and bringing it down into machine code that can't yet be run. So you cannot run something that's been compiled, a single file, until you link together all the libraries that it needs. Okay, so that's the idea. And .o means object file. That's a compiled single file. And we'll talk about that in just a second. So here are all the steps. The first one is making this assembly code. You'll never have to do this again in the class, but I want to show what it looks like. And then this is the compilation process. -C stands for compile only. Do not link together any libraries. So this .o makes something that cannot yet be run. And this final one, this -o essentially, is telling it to link together to make a final executable that you call a certain thing. Okay? And this is another example of linking when you have multiple things that you want to use. So let me give you several examples here. Let's make a new file with a main function. And I'll call it hello.cpp. And let's do cout hello world, new line, of course. Now let me show you all these processes. So G++-s. Let's see if I can put all these together, actually. The last one I can't really give you an example of, but hopefully the first three should make that one make sense. There we go. All right. This one, create assembly. Okay, so let's try out the assembly code creation. Oop, Come on. There we go. G++. Let's call it, let's say -s. And this will make a file in my current directory called shapes.s, and that is an assembly file. And this is what assembly for Intel processors or AMD processors looks like. This cool stuff. Move things, call functions, load things, weird, amazing things. This is your essentially machine code. All of these things get translated into one single instruction. Your computer knows how to jump. So that's assembly. It's cool. This next one creates, compiles to what we call object code, which is essentially machine code. This is the compiled machine code for a single .cpp file. Okay, so you can compile multiple .cpp files separately. That's the idea of separate compilation. All right, so here, this one will make G++-C, oh sorry, hello dot, oh darn, this should say .cpp. I am so sorry. I cannot change this at the moment. Should say hello.cpp here. Sorry about that. So this makes hello.o. So G++-C does what we say, this does the compilation process on just shapes. So it makes a machine code version of shapes, but we can't actually run that. It's just machine code for a single file. It doesn't know about printing because we need to link together those libraries. Compiles and links libraries. Okay? So starting from hello.cpp, we already know what this is going to do. It's going to output into an executable program called hello. But there is an intermediate stage where, if you've already compiled once into machine code, links only, because you've already compiled. So this will actually work. This won't actually recompile, it'll just run the linker to link together those final libraries that it needs to make the executable. -o hello shapes.o. And the -o hello can go before or after things, so I can put it also at the end here. -o hello, doesn't matter. So this will make /hello that I can then go and run. That's the idea here. This is only linking when you start from a precompiled thing, .o. And then the idea for separate compilation is this right here. -o hello.o library 1.o library 2.o links multiple precompiled libraries that you make. So I had a library called it, and I compiled it into library 1.o, and I had another one, library 2, that I compiled into library 2.o. I can give all of these to G++ to link together to make our final hello file, and that is the key. So let me write this. Separate compilation saves you time. It makes it so that if you split up your program, so that if you split up your program and make a change to a single file, you don't have to waste time recompiling the files you didn't change. They're already compiled in these .o files. You don't have to worry about recompiling them, and that might take a lot of time if you have a lot of code. It might take hours to compile things. That's happened to me in internships. So that's the idea. That's what separate compilation is, and this is the goal. That was the goal of this entire lesson about separate compilation. Okay? And so you can give all of these different kinds of libraries to G++ and have things work out well. Okay? So with all of that in mind, I want to talk about a way to make this process automated using this program called make and these files called makefiles. So once you have a lot of things to compile, it eventually gets very hairy to actually like keep track of, oh, I only need to recompile this one because that's all I changed, and then I'll give all of these other things to G++. This thing called make takes care of that for us. So let me set this up for us so that we understand what's about to happen. So this is my shapes.cpp file, and I'm going to make a library now for shapes, test-driven development, and drawing actual shapes, or testing the shapes that I've written. So this is the implementation of the shapes. So let's put this up here. Implementation of shapes. Of shape drawing functions. And then I'm going to make two other files. One is going to be tdd.cpp, and the other one is going to be test shapes, I think. Let's make sure. Yes, test shapes. .cpp. And so this is going to be the shape drawing code up here. And the test-driven development code is this assert true stuff. So that'll look like that, and it'll also contain the implementation of assert true. And don't worry, I'm going to separate these out into .h files in just a second. And we want our testing function to do the actual testing and hold the main function. So I'll put the main function in the test shapes.cpp file. Let's see here. Do I actually need anything else here? I'm not actually printing anything. I'm printing in tdd.cpp, so I need iostream there. Let's just actually include all these just for fun in all of them. Makes it easier for me that way. Okay, so the idea is we're now going to make header files for all of them except for test shapes, because this is just the main function. So I'm going to make a shapes.h with the declarations. Declarations of shape drawing functions, because all the declarations, I only need the declarations to compile a certain file, just one at a time, okay? Because that's the idea now. I'm going to compile single things at a time. Dun, dun, dun. Then the tdd.cpp needs to be split up into tdd.h that holds the declarations. All right, declarations of all those assert functions. And here is their implementation. And then test shapes does just this. It's going to, let's include it up here. It's going to include the draw triangle function, because we need that, and that lives in shapes.h. We only need the declaration to compile. We'll worry about linking later. That is the key here. We'll only include, copy and paste, these declarations in here, because that's all test shape needs to know to eventually run the draw triangle function, or to eventually run the assert true function. But that is outside of this file, and we won't compile those things with it. All right? So if we were to make a change to the shapes.cpp file, we wouldn't have to recompile tdd or test shapes. That is our goal. Okay? Now, if we change tdd.cpp or shapes.cpp, we don't have to recompile this file, and vice versa for the other two. And that's because this include is only including declarations, not implementations, which might change. Okay, so that's the key here. And now I can compile all these things separately. So I can make G++ -c shapes.cpp to make my shapes.o. I can do the same for tdd.cpp to make my tdd.o. Here they all are. Then I can do all that again for testshapes.cpp to make a testshapes.o. And oops, I think I did something wrong here. Let us find out. Let me go to the first error. What have I done wrong? Unknown name string. So it looks like I'm not using namespace std early enough. And I think my error was, what I should have done is put these includes in the actual header files. And then in the CPP files, I can pound include the headers as well. That would solve these things, because that way it'll see using namespace std before anything else. And then we'll include ourselves. Done that, and now it should work. Okie dokie. And now I can link them all together into a final thing called test shapes. So test shapes.o, tdd.o, shapes.o, and then I'll run my test shapes. And now I've separately compiled all of these things with the -c, remember? And I can bring them together. That was a lot of work though, and make automates this process. So we make these things called make files that tell us how to piece together these different programs and how we compile them to build our final complete program. And we're essentially writing a recipe for compilation. That's the idea here. And so when we run it, it'll use that recipe and it will only remake the things that need to be remade. So we can tell, instead of this big thing, we can say just make to the terminal and it'll run this thing called a make file that is going to do this all for us. And so this is the idea. I've mostly done this demo already. Let me go through it and make sure that it's all working. Just a single program. Yep, we've checked these boxes already. I'm happy about that. Let's look at some errors that we could possibly have in this case before we do make files. So I can have a compile time error, of course, by just forgetting something. Or doing something wrong, like triple equals. Why not? So let me try and compile testshapes.cpp. That's -c for just compile. Don't make a final executable. So here's a normal error for compilation. I won't make a final program for you because you did this wrong. And a link error is extra interesting. So remember that we needed tdd.o and shapes.o because we used those functions defined there in our shapes.cpp, or in our testshapes.cpp. So let's see what happens when I forget one of those. I'll get rid of shapes.o. So now I don't have access to the implementation for draw triangle. I have the declaration only, but that's not good enough. I don't know where the code is. Let me do that. Oh, oops, am I in the wrong directory? Dun, dun, dun. No, maybe I need to recompile. Sorry about that. Yeah, okay, here's a linker error now. It's saying, I don't know where draw triangle is because I know it exists from here, but I don't have the implementation because you did not link together that final shapes.o where that implementation compiled lives. Okay, that's the idea there. Let's see. Now let's start with just a simple make file. So, yes. That's the last of this first part. So, starting with a simple make file, let's go through this to see how we compile things. So let me write a make file rule for our hello.cpp. That's a lot easier. So for make files, you have to make one file, and the file name is very important. It has to be called makefile with a capital M. Okay? It lives in your current directory. Make files have to be called makefile. That's key. I'm gonna make this in bold. There. All right. So our makefile, we can have comments. This is a comment. Make is a different language than C++, and so you have different kinds of comments. It has that number sign that you're familiar with if you know Python. So this is a comment, and this is what a recipe in make looks like. It goes this thing called the target, which is what you want to make. And then you have a colon with some ingredients. Ingredient 1, ingredient 2, ingredient 3. These are the things that it takes to make this thing called target. And then step 1, then you hit enter, new line, and then you tab over. This is a tab here. Tab. Let me actually erase that. That's a new line and a tab. Tab is very important. And then you start now on this line right here, saying your first rule to make it. Step 1, to use the ingredients to make the target. And then step 2, and so on and so forth. And eventually you're going to usually be left with a file called target. And that's the idea here. And these are all tabs. Oops, that is nowhere near this second line. Tab. It's always tabbed over, okay? So let me go to, oops, no, come back. There we go. So target, ingredient 1, ingredient 2, ingredient 3, dot, 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 tab, step 1, tab, step 2, tab, dot, 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 until eventually you're left with a target. So what we want to do now is let's make a rule for hello to compile hello.cvp. So our target, the thing that we want to make, is going to be called hello. So that's what we want. Then a colon, how do we need it? What do we need in order to get it? So in order to make hello, we need hello.cpp to make hello. Okay, that's the idea. That's all we need. And then assuming we had that, let's tab over and write the steps involved to use this ingredient to make hello. And there's only one step, g++ hello.cpp into hello. Okay, that is the key. And now I just made a rule called hello. And I can say now, in my terminal, I can say make hello. And it'll find this rule called hello with that target name, and it'll run it, actually. So it'll run that thing, all those steps that it needed to do to make that final thing. Which is beautiful, isn't it? The first rule in your make file is special. You can just say make in the terminal, and it'll make the first rule. So instead of saying make hello, I can just say make, and it'll run the first one, because that one was hello. Okay? So now is where the fun stuff happens. So let's do what we were doing before for test shapes. So in the very end, we needed to bring together g++, test, compile into this thing called test shapes. And we wanted to use testshapes.o, testshapes.o, and tdd.o, okay? And that was our step. That was the process that we needed to use to make those things. But let's go back to the rule name. So this rule, our target should be test shapes. That's what we want. What we need in order to get it are these things. Let's put them there. And this is what we need to do to make test shapes given these things. Okay? Sure. Well, how do we make these things? And this is the very cool, this is the coolest bit about make, is if the recipe, if the ingredients of the recipe are not already made, it'll go and make those too. Okay? So, isn't this nice? Make is cool because it'll make the ingredients too if it knows how. Okay? So, all right, let's make a rule for test shapes.o. How do we make that? Well, we need testshapes.cpp in order to make it, And to go from testshapes.cpp to testshapes.o, we need to do g++-c testshapes.cpp. You see where I'm going with this? So let's do the same for shapes and for TDD. Okay, so the idea is if any of these didn't exist, like for example shapes.o, it would then go and use this rule to make it first. So let me remove the file shapes.o. Now it's no longer there. And so this make file will actually recompile shapes.o when I say make test shapes. Because it knows I required that. And it looks like something was wrong with tdd.o. And it needed to then make tdd, to make it from tdd.cpp. And then we also use this to make test shapes. And nothing was actually wrong with tdd.cpp. All that happened was I think I made a change in between compilation. I added that header thing, which didn't really change anything concrete, but I made a physical change to the file. So that is the key here. Let me now, I don't know, add an extra new line to shapes.cpp to pretend I changed it. Now, when I say make test shapes, it'll recompile just shapes.cpp because it saw that there was a change. It didn't recompile anything else. So now when I say make test shapes, it's going to say, oh, it's already up to date. But if I change something else, tdd.cpp, it'll then go and see, oh, well, I require an up-to-date tdd.o. Let me go and recompile that in order to make test shapes now. And so you can see it's always going to do just what it needs to do in order to make the final thing. It'll make the ingredients if it knows how. It won't do any extra work. It'll only make the stuff that it needs. It knows when things have changed as well, which is very powerful and very efficient. Okay, so I think that's everything that I want to say here. There are some fancier things to make, and I want to talk about those. So first of all, default rules. There are default make rules for making .o files and compiling one single .cpp file into a final executable. So make already has a make file made for you that it runs if you didn't give it something. So I can comment this out. This can actually be done with a default make rule. So I don't have to re-give it. So now let me remove hello. I can say make hello, and it'll run the default make rule to compile that. It looks like this. C++ is just a synonym for G++ in this case. So there are default rules. So every time I made something, every time I compiled something up to this point, I always said G++ hello.cpp -o hello. Well, I didn't actually have to do that. There's a default make rule that if I were to say make hello, it would actually run that default rule. I didn't even have to make my own makefile, and it would compile it for me. Same with these. There are default rules for making .o files. There are also default rules for making .o files. So I don't actually need any of these three. I'll just comment this one out for fun. So if I say remove test shapes.o, and I say make test shapes.o, it'll run this default rule again, okay? With some extra arguments. It's like, particularly call it test shapes.o. It's really unnecessary. And again, C++ is really G++. But it does the same thing. If I were to say make test shapes, it would use all those things, and it all still works. Okay? So that's beautiful. A few extra things. So you can have synonyms. You can have variables in make. And you can say things like, all right, my C compiler, CXX, is G++. And so now every time you say, instead of saying G++, I can say, let me actually keep this around. So the below is equivalent to the above. I can say, well, yeah, give me all this. But also, instead of G++, I might want to swap that out one day with a new compiler. There's two main C compilers, or C++ compilers. Let's just use whatever one I put up top. Could be G++, could be something else. And this will actually, if I use this $sign and a parentheses around this variable, it will replace it with what we said that we want it to be. Let me remove test shapes. Now make it. Okay? And I can also make some files like this, saying like, I don't know, binaries. The things that I'm about to make are, let's see here. I'm going to make something called hello. I'm also going to make something called test shapes. I'll space separate those. And now I can make a rule called clean, which gets rid of everything that I compiled. So it'll remove every .o file and also all my binaries. So make clean will go to that variable and replace binaries with what was there. Okay? And so now when I say make test shapes, I just got rid of all the .o files and everything else. So it'll recompile all that stuff from the start, using the default rule here, because I commented that one out, using the ones we gave here, and using our final rule. Okay? Now also, I can do things like this. There's a shortcut for the name of the target. Is equivalent to the target name, and $caret is equivalent to the ingredients. So in theory, I could do this. Target instead of test shapes, because that'll get replaced, as well as $caret instead of all of these, because that'll get replaced. Okay? So I'm doing this right now so that you don't get worried about it when you see this in your lab. Make clean, make test shapes, and let's wait for the final rule, because it's going to replace all those things that I said with exactly what I said that it would replace them with. So G++ came from CXX, $@ is test shapes, and $caret is all these things. So that is makefiles in a nutshell. And we have about 15 minutes left, and I want to get into now number conversion. So in those last 15 minutes, let's move away from makefiles and talk about numbers again. So let's talk about the numbers we know already. We like to work in base 10. That's decimals. And this is really nice for us as humans because that's what we think in. We have, well, let me ask you, why do you think we have 10, why we use base 10? And it just so happens that people think it's because we have 10 fingers. So if you were in The Simpsons, for example, where they have 8 fingers, maybe they would be using base 8. And there's also the numbers that our computer uses, which is in this thing called binary, which is called base 2, and it's made up of 1s and 0s. So that's what our numbers actually look like when we save them into our computer. They're just a bunch of 1s and 0s. They're not in decimal anymore, even though we type them like that into our programs. So let us talk about how we represent numbers in a certain base. So every position, every time we write another number to the left or the right of another, we are multiplying by a certain power of our base. So for example, if I had the number 155, and this is in base 10, the one that we know, and I'll specify the base by putting the subscript. This, if you remember from elementary school, you can expand this into 1 times 100 plus 5 times 50 plus 5 times, 5 times 10 plus 5 times 1. And you can expand this further into 1 times 10 squared plus 5 times 10 to the 0, and I hope you're seeing the pattern here, times 10 to the first, sorry, plus 5 times 10 to the 0. And then look where this base is popping up. every time we have a different digit, we're using a different power of the base. And that is the key. Okay? So, binary is base 2. So this is decimal. Decimal is base 10. Is base 10. The digits we work with, there are 10 of them, are 0, 1, all the way to 9. So we have 10 digits to work with. So binary is base 2. The digits we work with are, if you just follow the pattern, we get 2 to work with, so we have to choose starting at 0 and stopping at 1. So we're only using zeros and ones. Every time we have a digit, a binary digit is short for the word bit. So we'll say bit every time. So here's a binary number. It's made up of zeros and ones. 1, 0, 1, 1, base 2. So this is a bit, this is a bit. All of these are bits, a single digit. Bits take up some space in memory. That's exactly what your hard drive is storing in like electrical signals. And every time you have 8 bits, we call that a byte. Okay? So here is my example 4-bit number. And if you follow the pattern, you can expand this. If you go the opposite way, so this is, let's start with this one. It's 1 times 2 to the 0, right? Plus 1 times 2 to the 1. And now this one, 0, which doesn't really count, times 2 to the 2 plus 1, this final one, times 2 to the 3. So this is 2, 4, 8 plus 0 plus 2 plus 1. So that is equal to 11. Okay, so this is the binary number for 11 in base 10 now. We just converted from binary to decimal. Okay, and yeah, our data, these ones and zeros are really voltages. And every time we have a high voltage inside of our computer, it's a 1, and low voltages count as 0. So take a second now to convert this base 5 number into decimal, please. And then let me do it with you. So 101, base 5. So let's expand this. Let's start with the first digit. This is equal to 1 times 5, remember, that's the new base. 5 to the 0. Just like this was, here's the base a million times. Here's the base a million times for each digit. So here's the base, and we're going to show this 5 a million times. Okay, that's the fives, the ones place. Then we have our fives place, you can call it. 0 times 5 to the 1 plus, now this one, 1 times 5 to the 2. Remember, it's always one less than you might think. This is like the third digit over, but it's really to the second power. Remember that. And again, here are my 5s. So this is really 25 plus, let's see, so yeah, plus 1 equals, this is a base 5 number for 26 in decimal that we know and love. Okay? So get used to this idea of going between bases. Okay? So this is in fact 26, because it is 25 plus 1, and that's how we calculate that. All right. Now, one thing that we would like to do is to be able to go in both directions. So it's very easy to go from binary to decimal, like we talked about. So 1, 0, 1, 1, 0. Let's do that quickly. 1, 0, 1, 1, 0, base 2 equals what? Base 10? Well, let's figure that out. It is, I'm going to go quicker now. So this is times 2 to the 0, there's nothing there, plus times 2 to the 1, so that's 2 plus 2 squared plus 4 plus, no 8s, but a 16 equals 22, I think. Let me confirm that with Python. If you go into Python, you can say 0b, I think, for binary. Yeah, it's 22. Cool. Now, we want to be able to go the other way. And it's a bit more complicated to go from a decimal number that we know about to a different base. And in order to do that properly, let's talk about how we go and extract digits from a decimal number. So let's talk about digit extraction. Digit extraction. And let's see here. The idea about this is that every time we have a digit and we want to take it out of, let's say we had our 155 in decimal. What operations can you do to extract a single digit? Okay? How do I get the rightmost digit is the question. What operations can I do? What operation should I do to get the rightmost digit? Think about that. And it just so happens that the answer is modulo by 10, which, oh man, that's the base, isn't it? That's going to be important. So to get the rightmost digit, to get this 5, 155 mod 10 happens to be that 5. Okay, so I can get the rightmost digit. I can get the next one if I can just shift away that 5. If I can turn 155 into 15 by shifting this digit out. So what operation should I do to remove the rightmost digit? That is, turn 155 into 15. So think about that, and the answer is integer divide by the base, by 10. Not 10 factorial, by the way. So 155 integer divide by 10 gets rid of the decimal because it's 15.5, right? It's really now 15. Okay, so now I have this one to work with, and I can again mod by 10 to get the next digit, which is 5. And then I can again divide 15 by 10 to get this digit, equals 1. And then now I have all of the digits of 155 in base 10. This process works for any base, okay? Coming from decimal. It actually works coming from any base as long as you know how to divide in a certain base, but I think as humans we're used to dividing in base 10. So let's now go from 34 base 10 to something base 2. Let me show you how this works. The idea is we want to get the rightmost binary digit, not the 4, but the rightmost binary digit of 34. Okay, and we're going to modulo by the base that we want, which is 2. So the algorithm for base conversion involves repeated modulo and integer division by the base you're converting to. Okay? So in order to get the rightmost digit, you get the digits in reverse order, like I showed above. So in order to get the rightmost binary digit, the rightmost bit of 34, base 10 again, we're going to do mod 2 to 34, and it's an even number, so I'm going to get 0. So that's my rightmost digit. Okay? And now I need to shift right. I need to shift away that rightmost binary digit. And so what I need to do is to integer divide by the base. 34 divided by 2. That equals 17. 34 shifted in binary by 1 digit, 1 bit. So now I have 17 to work with, and I need to get the rightmost bit of it. Okay, that's the idea. So I'm going to do 17 mod 2. It's always the base. And this is an odd number, so I'm going to get a 1. It's my next digit. So I know this number ends in 1, 0, whatever it is. Okay? Then again, I'm going to keep going. Now 17 integer divide by 2 to shift that that last bit that I already got away. So this is going to be 8, I think. I think so. 8 times 2 is 16 plus, yeah, I think so. And all right, in order to get the rightmost bit of 8, I'm going to do 8 mod 2, even number, so I get a 0. And all right, let's shift that. 8 divided by 2 integer divide. That is 4. 4 mod 2 equals 0. It's even again. Okay, shift that. 4 divide 2 integer divide equals 2. All right, let's get the rightmost bit out of that. 2 mod 2 equals 0. It's even again. Let's shift that away now. 2 divided by 2 is 1. 1. Let's get the rightmost bit of that 1. 1 mod 2. Well, it should be just 1. And then, all right, let's shift that 1 away. 1 integer divided by 2 equals now 0. And this is my stopping condition. Stop. Uh-oh, my computer is going crazy. Sorry about this. So once you get to 0, you've ran out of number. Ran out of number to base convert. And so every time you took a mod, you have a digit. So this is our number. And I am very sorry because my computer is trying very hard to do something right now. It usually happens towards the end of these videos now, doesn't it? Every time I took a mod, I have a new digit. Okay? And so if I read all this out, let me check my time. If I read all this out, the answer is 1, 0, 0, 0, 1, 0. 0, 0, 1, 0. I hope I did that. 1, 0, 1 with 3 zeros, then 1, 0. And we can check this by converting this base 2 back into decimal. We can check that we did it right and make sure that it is, in fact, 34. And I'll do this quick. So 1 plus, so we have 2 plus 4, 8, 16, 32. 2 plus 32. Yeah, it does actually equal 34. And you can try that yourself. So that is going the other way. That repeated modulo and integer division. So as long as you follow this process, starting from a decimal number, going to any base, remember that the base is what you're moduloing by and integer dividing by. It's always that base. Then you'll get the digits of this number in reverse order. Okay? And once you hit 0, once you're finally out of digits to convert, then you can stop and just read them off. Okay? And I think we're a bit out of time now. I think if I check my stopwatch, that is enough time for one lecture. I have 3 minutes left technically, but I might need to squeeze something extra in. So that's where I'm going to stop for now, and I will see you next time. Let me go back to the recording.